If you do have special dietary requirements, please make sure to see us. For the dinner tomorrow, that's right. Because we need to finalize this with the restaurant, so please see us in the coffee break to make sure that your dietary requirement is registered correctly. And now we start. Our first speaker of the afternoon session is Mohamed, and he will talk about random matrix theory for big data and machine learning.
All right, thanks. So, hi everyone, thanks for being here. Actually, I'm Mohamed. I'm a PhD student. I'm starting just my second year of PhD, working on random matrix theory for big data and machine learning. So I'm supervised by Mohamed, who is present here, and Romain Couillet from Central Seddik. So thanks, Guy, for inviting us to the workshop. So it's really exciting to hear about physics and stuff. So we are not physicians, but we'll try to give you some insights about random matrix theory that we apply to machine learning. So this is the outline of the presentation. In the beginning, we will have a brief introduction to the subject, and then move on to different concepts concerning the models we use, random matrix models we use for machine learning. And at the end, we will discuss some universality aspects that are really essential when we want to handle real data so in real applications. All right, so in machine learning, we are given data. So it's a collection of observations of dimension ICTP, and we have n, which is the number of data. So I want you to keep these notations in mind. P is the dimension of each of the features, and n is the number of data that we observe, because it will be the two quantities that we will repeat through the presentation. So in machine learning, we aim at doing different tasks that are regression, classification, and clustering, etc. So, and at the heart of these tasks, we compute similarities. So we compute similarities between our data. And the example of similarity is just the inner product between the data, and this, quite naturally, we construct what we call the gram matrix, and it's also the V-shard matrix, so it's just X transpose X. So this matrix appears quite naturally in machine learning. And the question that we give is how does matrix behave? Sorry. So actually, random matrix theory gives us some answers about this question. And in particular, the behavior of this matrix depends on the two quantities that I introduced, P and N, the dimension of our data and the number of data that we observe. And in machine learning, we also face what we call large and numerous data. For example, the ImageNet dataset is a huge dataset with the dimension of each data of each image is about 150,000, and we have got a lot of these images. So, and this defines exactly what we call the random matrix regime, random matrix theory. So, meaning that both the dimension and number of data tend to infinity, but with scaling the ratio between these two quantities. All right, so now we'll talk about the behavior of this gram matrix. So if we assume that we are given data that are distributed as a multinormal distribution with identity covariance and mean 0, and when we observe the spectrum of the gram matrix, we will see a spread of eigenvalues in the vicinity of of the value 1, for example, for the identity matrix. And this spread of eigenvalues, so we can quantify it by what we call the Marchand-Pasteur law. I don't know if you guys have any idea about this tools or no. So I will give just a brief introduction to what is the Marchand-Pasteur law. So what we aim here is to characterize the distribution of eigenvalues. And we start by defining what we call the empirical spectral density. So it's this quantity here. It's just the mean over the Dirac at each point at each eigenvalue. And the Marchand-Pasteur law tells us, so it's the following results, is that the ACD of the Gram matrix will tend to almost surely to a measure, to a deterministic measure which has as density this function here. So, and this is how what it looks. So when we draw just a density and function of it for different values of C, so C is just a ratio P over N, we will get different behaviors of the Gram matrix in terms of the spectrum. So this is the central or the fundamental tool that we will be using in the following. So actually in machine learning, we don't have just covariance matrix or data with zero mean, but we have a kind of clusters. So let's say we have two clusters. We have two classes. The first one is parameterized by a mean plus m, and the second one is by minus n. So we have two classes like that. And this matrix can be written in the following way. So it's just this quantity where y is just the vector of labels. So it's +1 for the first class and -1 for the other. And z is a random matrix with random IID entries, normal IID entries. And when we look to the Gram matrix, it has the following formula. So it's a Laurent transformation plus the Gram matrix with zero mean that we just saw before, and plus other terms that will convert to zero. So we are interested in these two quantities here. And in terms of spectrum, so we have got, so the noise part here will be expressed by this spreading of eigenvalues, this bulk of eigenvalues, which is quantified by the Marchand-Pasteur law. And we will have an isolated eigenvalue, which will be visible if the distance between means is bigger than a certain threshold. So we have got this, what we call a phase transition. So if m is bigger than square root of c, so we will see this spike appears beyond the bulk. And this is the term that contains information about clustering, or if we want to do classification. In particular, we look to the corresponding eigenvector. So it contains information about classes. So we got here the first class and the second class. So in terms of classification, we have just to take this vector and to see which element belongs to which class. All right. So actually, this model is what we call the spiked models in the random matrix theory community, and is given by the result of Bate and Silverstein. So it quantifies exactly the conversion eigenvalue of the conversion value of the largest eigenvalue. So we have this expression that is, it will be bigger than 1 plus square root of c squared. So this is the right-hand side of the bulk value, and it's visible if we have this phase transition phenomenon. we got the similar result for the eigenvectors. So this is not important, but we see that the estimated eigenvector will converge to the true one with this rate. So we have a kind of phase transition also for the eigenvalue, for the corresponding eigenvalue. So which is the quantity of interest if we can do, we want to do classification. All right. So now in machine learning, we don't use linear methods like gram matrix, but we apply some kernels to which are non-linear methods. Actually, neural networks can be seen as general matrices also because it generates a representation that can be seen as a kernel. All right, so here, if we are interested in kernel sputtering, so the problem statement of kernel sputter clustering is given data, the objective is to compute similarity between data, is to cluster those data on different clusters. And we do this based on a kernel matrix that we construct through a kernel function f in the following way. So it can be a similarity distance between the sorry?
What would be in the ImageNet example you were saying? What would be similarity classes?
In the ImageNet, it will be just the classes of ImageNet, so bird, car, etc. So these are the classes. But here we are interested in unsupervised classification problems. So we just see the data and we will see if we can do some classification about this data. All right. So when we look to this matrix in the small dimension perspective, we see that we can do classification. So it has the following behavior. So we can observe that for a certain class, C1, for example, that huge values of this general matrix will see that these elements belong to the same class and so on. So this is the intuition from small dimension. And yeah, the intuition is that K is a low-rank matrix with eigenvectors containing information about classes. So this is mainly the intuition behind this problem. All right, so if we look at this problem, we consider some model on our data. So now we consider a model by adding different means for each class and different covariance matrices. If we introduce this following quantities here, so M is just the average of our means, and C is the same for the covariances. And we work on the following assumptions. So as n tends to infinity, so we consider the random matrix regime as I introduced in the beginning. So we consider that we have this growth assumption. So P over N converges to a certain quantity C0, and NL here is the number of the each i's belonging to the class CL, for example. We consider the following assumption on the means. So this is what we consider this assumption to make the clustering a bit harder in high dimension, because if we don't control the means, it means when we go to in high dimension, it means that the different clusters will spread off, so it will be an easy problem to resolve. But if we control the mean on the following way, so all the clusters are concentrated in certain region in space as P tends to infinity. I don't know if it's okay, but all right. So, and we have the same growth rates on the covariances. So given this model, so the intuition that we have in small dimension is the following, as I presented. But when we look at the things in high dimension, all the classes are similar. So we have this observation. If you just do simulation on MATLAB or Python by applying a kernel matrix in small dimension for Gaussian vectors, and in high dimension, you will see that the kernel matrix looks like this. So this comes from the following observation, that in high dimension, whether the two data are in the same class or not, they will converge to a constant value which is 2 over p times of the covariance matrix. So the between and within class vectors are equidistant in high dimension. So based on this observation, we can Taylor expand the kernel matrix interwise in the following way. And we got this similar structure as before. So we got a Laurent information plus a noise depending on our kernel function f. All right? And these are the following quantities. So the matrix A depends on the means and the covariances here. So the matrix J is here towards, sorry, spoke some French. So it corresponds to the canonical canonical classes. So it's I don't know if I can draw something here. So G1, for example, is a vector with 1 for the class C1 and 0 for the other classes. All right. So M is just a matrix containing different means. T and so these two matrices, this vector and matrix, they depend on the covariances. All right. So essentially, what we observe that in high dimension, the behavior of the kernel matrix is essentially a Laurent matrix plus something that behaves like a Wishart matrix or a ground matrix that we introduced before. So now when we apply this to, say, Emily's data, for example, digits, these are the leading 4 eigenvectors of the kernel matrix. We see that, and these are the theoretical ones that we estimate based on this approximation. So we see that there is a fit between theory and practice, but these images are not Gaussian. So it's quite surprising because we consider the Gaussian assumption on data, and we have a kind of result that works for complex data here. So this suggests a kind of universality of these methods, kernel spectral clustering, and in the following I will explain.
What were the broken lines?
The blue lines here?
The broken blue lines.
Here, it's a standard deviation. So actually, with this formula, we can estimate the mean and different moments. Essentially, standard deviation will be. So it works quite well for the largest eigenvectors, and the others, it's it's like, I don't know.
So what you plot on this on the x-axis essentially, or what is the red line?
All right. Okay. So actually, we compute the kernel matrix K here. If we rearrange our data as I introduced here. So let's say in the beginning we put just the data from the same class and so on. And we compute the kernel matrix from this data, and we look at the dominant eigenvectors. So this is the first eigenvector plotted in function of the dimension. It's a number of data here. So K is a n by n matrix. So he's is a vector in Rn actually. And when we plot it, this is the first one, second one, and so on. Right.
What is M for MNIST?
MNIST?
Yeah, what is N? How many do you have for the data set?
Yeah, actually, it's the dimension. It's 70, 100. I don't know. Yeah, and it's just 100. So 100 by times 100 matrix. All right, and this is n, and the dimension is 785. Yeah, I should put the values here. All right, now that it works for real data, we will see why does it work. And the reason is the following. So real data are unlikely close to Gaussian. So we can consider this model for real data. However, we can use what we call generative adversarial networks. I don't know if you have some background about that. But essentially, it is possible to reconstruct some synthetic and realistic data through the application of consecutive Lipschitz operations to Gaussian vectors. So we got a neural network that does so a consecutive operations, convolutions plus activation functions, and this is our Lipschitz operations. And applied to Gaussian vectors, we can generate data that look real. On the other hand, so this comes from the concentration of measure phenomenon. So if we define a concentrated vector in the following way, so for any Lipschitz function, we have the concentration property here, which we just denote on the following way. As an example, an application, a Lipschitz application to a Gaussian vector is a concentrated vector in the sense of this definition. So it's a result from Ludo. These two observations suggest that considering data as concentrated vectors is quite a good model to see how this works. All right, so we make this assumption. We consider that our different clusters are now concentrated vectors. And based on the same assumptions on the means and covariances, we still have a kind of Martian to Pasteur law for concentrated vectors now. So this is a generalization of the Martian to Pasteur law for a model where we have covariances. So if we take all the SCL equal to identity, we got here just the Martian to Pasteur law that we saw before. All right? But with structures on data, by adding covariances, we have this. So actually it depends, it's a solution of a fixed point equation that gives us the density of eigenvalues. Right. So essentially we have the same behavior of the Gram matrix. All right. So by considering now the concentrated assumption on our data, we still have the same observation. So the between and within class vectors are quite equidistant in high dimension. We have this, and by the same argument, using a Taylor expansion, we have this information plus noise structure. And the difference between the Gaussian assumption and the concentrated assumption appears in the fourth order moments that are non-informative about places. So we are just interested in what is happening here, but we don't lose too much by considering the concentrated assumption on data rather than the Gaussian assumption. So just to recall the different quantities here. All right, now we apply this to GAN-generated images. So actually, this is a brief recall about what are generative adversarial networks. So we want to generate data that are close to a certain data set, and it works on the following way. We start from a random noise, and we optimize two networks, a generator and distributor, with the following objective. So the distributor does a classification task by classifying real images and generated images as real label, and fake images, generated images, as fake images. And the generator tries to minimize this objective by producing images that look like real images. So there is an equilibrium of this, the train of these two networks. And at the end, the generator will generate images that look like the images on our dataset. So once the generator trained, we generate images on the following way. We start by applying a noise vector, a Gaussian vector, to generator and generate images. So it looks like this. This are some images generated by a GAN. So I don't know if it convinces you, but this is a dog and so on, hamburger. All right. So this is a result from the DeepMind team from just last year, and it's quite surprising. Now in computer vision, we don't use those images directly. We use what we call a CNN representation of images. So we add, so mainly it's just the before last layer of our pre-trained network that does classification. And so here we will generate data as the representation of images generated by a GAN. So we still have a Lipschitz operation between the Gaussian vectors and the concentrated vectors. So its eyes are concentrated vectors as we have just defined. And this is there are some results. So in black, it's the spectrum of the real kernel matrix, and in red is the spectrum of our approximation using the Tyler expansion. And the three spectrums are at different training of the CNN network, the representation network. All right. So once the generator is trained, we train the CNN representation network, and these are the different training phases. So this corresponds to 0 training of the CNN, after 5 epochs training, and after 40 epochs training. Yeah.
So sometimes GANs work better than in other cases. So
yes.
So is there a way of seeing this on these distributions in the sense of, you know?
Yeah. Actually, what we have from random matrix theory is we can characterize the distance between the spike and the belt, and this characterizes how well the images are close to the classes we want to generate. All right. So it quantifies actually this how well the network separates our data, and etc. All right. So these are the eigenvalues. So we can see that we have informative spikes here and spreading of eigenvalues as we have seen before in the linear case. And we look at the eigenvectors now. So these are the red one is the So actually there is two curves here, in red and black, and they are superposed, so we can differentiate it. But this is the first eigenvector and the second one for the different training phases. And when we put them together, we get our clusters. So these are, and actually with random matrix theory, we can quantify that here we don't have a good classification, and here we have a quite good classification. All right?
So did you trained again with ImageNet?
No, it's just an example with Cypher, but these are images from the ImageNet, but I will do it for ImageNet in the coming weeks. All right.
Okay, so you trained some inputs there?
Yeah. Actually, these are the true images generated by the gun I use it. So we can see a car here, a plane, and a bird, actually.
But the CNN then does the classification?
Does the classification on these?
Only on the GAN-generated images?
Yeah.
Or on also the ones which...
No, on the GAN-generated images. Okay. So these are the results for the GAN-generated images, and we see the same behavior for the real images as we can see here.
And the GAN use CFAR? That was one of your questions. What was the input to the GAN?
Yeah, it's CFAR, that is it, yeah.
And what was the difference between A, B, C, D, E, F?
Yeah, all right. So here is the CNN training, I have two networks actually. I have the generator and the representation network. So the generator is trained. So we have a generator that generates images. And the representation network is actually a CNN that is trained to classify the different images. And we take the before last layer as the representation for all images. Right. Typically, this representation is 124 dimensional. Right. So these are the results for the GAN-generated images, and we have exactly the same behavior, right, for the real images. Okay. And as I said, through random matrix theory, we can quantify based on the Taylor-Pension argument. We can quantify whether we have a good classification or a bad classification. All right. So to summarize, random matrix theory allows for the theoretical understanding of machine learning methods. So this is just the example of kernel spectral clustering, but we can apply the same strategy for other methods. So we can model real data as concentrated vectors because we saw that it fits with what we observe. So this means that RMT is quite relevant for the study of machine learning methods. So if you guys are interested in doing some RMT for machine learning, just it's really interesting. So as per perspective, so I have following tasks to do. So generalizing to classification regression problems. So here I have just done the clustering problem, but we can generalize it, of course, to other problems. And with a colleague of mine, we want to use the concentration framework to understand the dynamics of neural networks and GANs in the future. So thank you for your attention.